Okay. Hello, everybody. We are on part 3 of NeurIPS Recap 2023 Trends in AI. I'm Nick, and we're going to the exciting part, my personal favorite, mathematics, reasoning, and large language models. Okay. So, I think 2015 or 2016, we were introduced to this paper by Google. It was called Deep Math, Deep Sequence Model for Premise Selection. So in a mathematical proof, you're at the state and you need to find out what other premise or tactic should I use in order to go to the next step. And the art over there is to predict, from thousands or hundreds of thousands or millions of premises and tactics, which one you should pick or try, because you don't want to brute force all of them. So there was this, model where it was character-based, wherever the states that you were, and it was trying to predict the next premise. Things haven't changed that much, except for the fact that we're using, instead of RNN, language models right now. Okay, so and now we have the introduction of the Lean, the program language and theory improver, which we're going to talk about that a lot. So these are the papers again, and I feel like we should talk about the DeepMinds. That's a very recent paper, where they did talk about proving. Actually not very since 2021, but anyway, they proved that they managed to prove theorems in knot theory that they weren't proved before. I think they came up with another one more recently. So, but that wasn't part of the conference. Now, first of all, let's talk about what is formal theory proving. So, in formal theory proving, the math is represented as a program, like C, whatever, like commands. Okay. And the nice thing about that, because we're all used to proving a theorem based on symbols, okay, LaTeX symbols, let's say. That's the formalization. But it's very difficult for a computer to formally, deterministically tell you if your proof is correct. But if you run it if you write it as commands, like as a programming language, then it can actually, with 100% confidence, tell you that your proof is correct or your proof is wrong. Okay, and the problem is that right now most of the language models have been trained into doing mathematical reasoning with symbols. You can go to ChatGPT and ask, to prove the Pythagorean theorem. It will just use words and symbols, but we would like the language models to output code that a theorem prover like Lean can verify. And you probably have seen that LLMs are pretty good at high school math level. I think they'll probably get into most of the universities. They scored the 89th percentile for SAT math. And, there's systems like Minerva, MetaMath, Wizard Math, Mammoth, Lemma, that they produce nice symbolic proofs. Again, for you, Minerva was done by Google. It was proprietary, and Lemma was an effort to create an open source version of that and use less parameters. So they basically say that with less parameters, they can get the same behavior. We're going to see it later on what they did in order to get there. Now, so we did talk about informal versus formal mathematical reasoning. One uses simple, the other uses programs. And even for us humans, it's really hard to, stamp and say that this proof is correct. So Quanta Magazine, it was one of my favorites for math and sciences. There was this article, Titans of Mathematics Clash Over Epic Proof of ABC Conjecture. People take years, in order to, and they're not even sure, because these are like 200 pages proofs. Like the Fermat last theorem, I think it took about 2 or 3 years full time from 2 mathematicians to go through that and verify it. You know, you can believe like these people like dropped everything they were doing, and they had to prove. And the problem is that I don't think there were other people on the planet that could have done that. There were very few people on the planet that could have verified. So we need to find a way to formalize it. But if the mathematicians were trained to write their proofs in code, you know, you can just feed it to Lynn or Isabel or Cole in order to do the proof. These are interactive systems where you give them the next command and they say yes, move. In some cases, they can also recommend changes. You know, despite the fact that these are the old ones and they have formal libraries, big ones, 250, more than 100K. Lean is the most recent, and I don't know much about it, but it becomes more popular. Part of the popularity has to do with Terence Tao, who's a field medalist, and he's trying to, you know, put more and more proofs into that system. But it doesn't really matter. They're all very, very good. And again, the way that the theory proving is working is really simple. You start from, you know, your proof state, what you have, and then you have this oracle. This is like a language model that basically trying to tell you where to go next, you know, which tactic you have to use. Now, if you're in geometry, you will say, draw this extra line, or trying to prove the congruence of these triangles and then the congruence of another triangle. You know, revoke some premises that, retrieve some premises that should be used, and then go to the next step. But as you can understand, there's multiple, you know, it can't tell you, doesn't know what's the right one. So it starts kind of like suggesting multiple tactics, which means that, you know, now you have different paths to follow. So you can do a best first search, or you can do the hypertree proof search. And there's other people that they say, you don't really need to do search. There's other techniques. It doesn't matter, you know. Then you got the premise selection. Again, it's a little bit tactic and premise. There are different things. And that's a system that does that. And in some cases, if you really have to search among several tactics and premises, you use the good old retrieve and augmented the RAG, you know, generation, also used in theory improver. If you want to learn more, you know, you should read the Lean Dojo. That is using RAG over here. And one of the problems that we're having when we train the systems is that we have a lot of data when it comes to informal theory improvers. Again, informal proofs are the things you do with symbols. You can find plenty of web pages. And, you know, there is a system that what it does is, you know, it takes, you know, it goes and crawls the web, like the Open Web Math, that it crawls all these proofs. It uses a language model to convert them to code. You know, it takes them to a theory improver. The theory improver will say, well, that proof failed, so there's probably something wrong, might be syntactically wrong. Or so now some of them are going to be done correctly. Now you use them, you go, you fine tune your language model again, or you put in the pre-training data and you keep running this loop. And here are some projects that they're working in that direction. As I said, Lemma that we saw before does the same thing. And you know, here are some statistics. So there's only 25%, you know, that it gets with the first, and then it keeps driving that loop. Now, we talked about mathematical proofs, but as I said in the beginning, these systems are also excellent for other types of proof. And you know, the proof that we want, we are in the software business, is verifying our code that is correct and doesn't have bugs. So this is an old technique, you know, like a lot of people do that, code verification. They've done that. And it turns out that you can take some Copilot code and you can basically it can generate some cases for you. You give it some examples, but that doesn't mean that the code is, if it passes some testing examples, that the code is correct. You really need to verify that it's correct. So there's the whole community that comes from the software development life cycle. When you take requirements, you design, you implement, you verify, you maintain. And the verification process is basically, you have to create assertions about what should happen. Like, this thing should be invariant, this thing should never be negative, or something. Like, you have to prove that it will never be negative, it will never be out of bounds, and things like that. And what happens, like, you have this cycle because you don't really know all the assertions. Like, what is correct is something that you have to do. But does anyone actually do this? It's a very, tedious process. And there are, big companies, like, you can imagine Airbus, and Google and others. They actually have to do that for pieces of their code that are very critical. But now it's prohibitively difficult. It says that proof is about 8 times bigger than the compiler code, 3 person years of work. In some cases, 11 person years of work. It says virtually all software that ships today is unverified, and that's the problem. So, they do some verification, but they can't verify everything. And this is kind of like an overview of current tools: the Z3, the Daphne, the Cockhammer. And there is these people that they call like proof engineers, that they do that. How well does this work for proof software of software correctness? And they say success rate is 30%. Yes, are only easy proofs being synthesized? Failing proof means that your code is not verified. We need new methods for the future. There's, if you have an interest in that field, you should go to that talk and see the details. And the problem over here is like it's like this auto formalization, and that's where the LLM comes. That basically tells you what generates the assertions about what the code needs to do. So there is, there are papers over here. So here's the proof engineer. They're just like us. I don't know. I felt tempted to try that as a future career. So the point is that they use LLMs. There's this paper called the Clover Paradigm, where it shows how you can run, this bootstrapping technique of generating code, generating more verification assertions, and going back and forth, looking at the comments and all that stuff. Okay, so that was part of the tutorial. Now we're going to the math AI, the third workshop on mathematical reasoning and AI. The idea over here, let me ground it to something that you probably know, the chain of thoughts, where when you go to when you ask a question, you encourage the language model to give you the steps, because it turns out that if it gives you the steps, it does a better job at answering the question rather than trying to give it at once. Something inspired by how we humans, do. We don't try to get with the answer, we're trying to break it into steps. Now, this is kind of like, this is a paper from Google Research and Stanford, where they talk about this self-taught reasoner, bootstrapping reasoning with reasoning, where you basically brainstorm and you say, well, start giving me questions and multiple choice answers, and show me which one is correct and tell me why it is correct. And then if it's not correct, generate others. So this is one technique. We give, you can also give it hints. So that's kind of like a human in the loop bootstrapping process. And that's kind of similar to something else that people use. That's kind of like the analogical reasoning, a paper from DeepMind. It goes back to the famous How to Solve It by Polya. They give a reference over here. And the idea is, before you answer, think about some analogies, put them in the context, and try again. And it turns out that this works better than a chain of thought. I won't go through the examples, but I have them here. You can go back to the slides and look at them. And here's the benchmark that they show, some significant jumps in the results. Again, you can look more at that. And they do make a point that analogical reasoning inherently relies on the ability of perceiving similarities between dissimilar problems at the surface level and drawing abstractions. That they claim that there's some level of abstraction over there. Now, from my personal experience, it turns out, and we're going to see that later, when it comes down to, let's say, natural language to SQL generation, showing some examples or retrieving some examples boosts a lot the performance. You can see the takeaways here, and here's part of the literature on analogical thinking. Okay, so now there's a different direction that I want to take. There's two presentations that they touch upon the same thing, which is, what problems can transformers generalize, or in other words, what algorithms can transformers learn? So let me go back 20 years ago, 30 years ago, when the two-layer perceptron was invented. People said that it can model the XOR function exactly. So there were some weights. Actually, I think it's an exercise in introductory deep learning classes, like find the weight so that it responds correctly to the XOR function, implement the XOR function. So there was a class of Boolean functions that a multi-layer perceptron would answer exactly 100%. So what we don't realize that the transformers, there's a class of problems that you can represent exactly, reasoning problems that they can solve with 100% accuracy. So the conjecture over here is that if they can represent an algorithm, then they can achieve better regularization. So what they did is they created this language called RASP-L, which is an extension of another language called RASP. Okay, well, basically, this is a language like, if you can take that program and translate it to a transformer that executes that exactly. Okay, that's very interesting. So and here's the paper that talks about the RASP extension, again, that tried to answer what algorithms can transformers learn. And why do we care about generalization? So the next paper comes exactly with that problem. AI can learn from data, but can it learn to reason? Okay, the paradox of learning to reason from data. And they said, actually, it doesn't really learn end-to-end reasoning. And it talks about architectures for reasoning, logical, probabilistic reasoning. That's kind of like the second part. We're going to see that. So what they discovered here is that for a BERT model with n layers and 12 attention heads by construction, there exists a set of parameters such that the model can correctly solve any reasoning problem in simple logic that requires at most n-2 steps in reasoning. So, this group over here, my good friend Guy, and co-worker, do not, they didn't invent their own language, but they said, we know a class of problems I can represent exactly. So what they did is they went and they represented, they generated data from these reasoning tasks, and these reasoning tasks generalized really well. But then they thought that if we change the domain and we have to do the same task, it should also learn to generalize. But the model wasn't generalizing. So they were wondering, did it learn the logic or did it learn something else? So they did a very clever experiment. So they said, okay, here's the problem we're having. We're going to put the exact weights that solve this problem. Okay, so we don't pass the data, it solves really well. Now, what we're gonna do is we're gonna try to continue training, or to start training that transformer from that state. So you would imagine that if it's like a stable state, if you put the data that they're supposed to fit in that task, that the transformer shouldn't move from there. But here you see the expression of key is that the model started drifting and it learned a different transformer. It learned a transformer that was learning the correlations between the data. Now you have to understand, that's easy to imagine that any logical task will create data that they have correlations. That's part of logic, to create, correlations between data. So basically, stochastic random descent was unlearning the transformer which was supposed to generalize, and it was learning something else. So it was learning the correlations between the data. And here's where I started thinking and saying, well, are we being, why are we being surprised? We all learned from that book all the elements of statistical learning. So we are training it in statistical way. Did we expect something better? Maybe we're using the wrong paradigm for training this data, because if you learn it, if you teach it statistically, then it will learn statistically. Okay, but I don't know. Is it impossible for logic to emerge from statistics? We don't know, because our experience, when you go to school, the teacher tells you about how the planets move. It doesn't give you dots and then you learn the Newton's law. You're forced to learn the Newton law, and somehow you code it into your brain. And when somebody asks you about the planet movement, you don't start generating data, like you go directly over there. You never, like, there's other cases where we learn the correlations. Think about statistical bias and stereotyping. Okay, we're very good at that. But we also learn most of the time the logic behind things. And so the question is, what is the architecture that creates logic from statistical observations, except for the human brain? Because I don't know, Kepler or Newton, they did learn from statistical observations and they created logic. And I'm just going to take one further later, since this is a presentation about brainstorming and being a little bit more relaxed. Would that be the definition of AGI? Learning from statistical, data logic? Oh, interesting questions. Now, for those of you who know Guy's research, he's very keen on probabilistic circuits, which is a way of tractable probabilistic models, the way of injecting logic over there. So again, language model, it's a probabilistic model. He took another probabilistic model where he knows how to use logic, and he put them together, and now he created this nice gelato system where he can actually enforce logical constraints to language models. And then he did the same thing for other Gen models, Gen AI models, like diffusion for images, and he called that tiramisu. So we all know that Guy loves sweets. He has a sweet tooth. And he was basically trying to enforce, some constraints that there have to be like two eyes here in this arc, or, some continuity that comes out of logic. Definitely, if you're interested, go and read the papers. Very good. Now, there was also this presentation which I couldn't find the references, and I'm not sure I could follow that much the presentation, where they talk about a transformer that uses something called tensor product networks, where they're able to inject the logic directly into the transformer. It's not maybe it does have attention, but it has something else as well. But I'm just mentioning that out of completeness. I would really like to follow up and find the papers that talk more in detail about that, because again, this is in the same direction, putting logic in the transformer. And now we're going to take a break. We finished part 3, and in the next one we're going to talk about LLMs for tabular data and some other smaller topics, and conclude our presentation about NeurIPS 2023.